It is time for a new unit here in PCH. We got polar coordinates, all right? 9.1. I'm pumped. I'm excited. I love polar coordinates. So one of my favorite parts about polar coordinates is we're going to bring back quite a bit of our special right triangles from honors geometry. And you know how much I love honors geometry. So let's get right to it. So if we want to solve some of these special right triangle situations, let me get a marker going here. We'll go purple. All right, so I've got a 45, 45, 90 triangle here for the first one. Well, I know that my legs are going to be congruent, 8 and 8. And if I do remember correctly, this would be an 8 root 2. Cool. If you want to jot down your 45, 45, 90 triangle, we got 1x, 1x, x root 2. Beautiful. All righty. This next one, looks like we got ourselves a little square action, right? All sides are congruent, 4 right angles, that's a square. So if that is 10 for my diagonal, I could divide by root 2 and rationalize, so I'd get 5 root 2 once I've simplified for my x value on that one. I did 10 divided by root 2, then I rationalized to give me 10 root 2 over 2. Which simplifies down to 5 root 2. We're going to want to be quick with these because they're going to be minor parts of a more complex problem. Okay? Now for this last one here, I've got 8 for my side. If one of those angles is 60 and the other one's 90, I know that's 30, so it's across my 30-degree angle side. If I were to draw up that right triangle, that special right triangle, 30, 60, 90, I know this is my 1x, this is my x root 3, and this is my 2x side. Again, I'm playing back into honors geometry here. So I'd end up with, well, x would be 8 root 3. And then this would be, here we'd have 16 for that one. Cool, cool. I like it. Wonderful and fantastic. Okay. Shall we continue? I think we shall. So one thing that's different about this is that we're going to be dealing with a different coordinate plane, okay? We've been dealing with the Cartesian coordinate grid or a rectangular plane for basically your entire mathematical career. We haven't known anything really different. So here's what we're going to do. We're going to graph a point P, 1 root 3 on a rectangular coordinate plane. And we're going to end up relating this now into our polar coordinate system. So if I graph 1 comma root 3, I've got, let's say this is going to be 1, and then I know root 3 is a little bit larger than 1. It's going to be more up here, so I'd be right there. This would be 1 comma root 3. Okay, cool. Now one thing that I can do with this and how we're going to relate this to polar coordinates is that first part. What is the length of OP? So if O is my origin and this is point P here, what is this length? Well, what if I were to draw in a triangle here? Because let's think here, I've got 1 for my side length for x. So this is a length of 1. And then this is a length of root 3, right? I went over 1. I went up root 3. So those are my side lengths. Aren't those the numbers for a special right triangle, 30, 60, 90? So that makes this length going to be 2. Okay, so I got 2 for that, right? Either I could use Pythagorean Theorem, 1 squared plus root 3 squared equals, x squared, or my hypotenuse squared, whatever you want to call it. Or I recognize the 30, 60, 90. And actually what's even more helpful here is that, well, what is the angle that OP makes with the x-axis? Meaning, what is this angle right here? Well, that's across from my root 3. That's just going to be a 60-degree angle, or pi over 3. So the way in which we name our polar coordinates, is by radius and by the angle that it makes with that positive, in this case, x-axis, which will have different words for these things, different vocab in the future here. So the radius here is 2, and our angle would be pi over 3, or 60 degrees. Look at that. We just wrote our first polar coordinate. So this would be r comma theta. Okay? That's all there's to it for this part right here. Obviously, there's a lot more to polar. That's not all there is to it. But that's our start. All right? So the radius, the distance away from the origin there, and then our angle that it makes with the positive x-axis. And again, the origin, positive x-axis, these are going to have different words here in just a sec. All right. So the polar coordinate system consists of a fixed point called the pole, right? That's similar to the origin. As I said, we're going to have different words here. And a fixed ray along the positive x-axis in rectangular coordinates, right? That's what I said. We're going to call it the polar axis. So the x-axis is now the polar axis. The origin is now our pole. All right. So you're going to hear those words used. You should know what they mean. All right. A polar coordinate is made of on a grid that shows concentric circles. So what you're going to see here in a little bit is you're going to see a graph, and rather than just this, you'll see concentric circles going out like oftentimes one radius at a time, and then we'll have our angle markings along those, so on and so forth. Okay, so we'll see that here in a little bit, a much neater drawing as well. So each point in that polar coordinate system is identified by its distance from the pole. So that was our hypotenuse of that special right triangle we just had, right? And that's our r coordinate, r comma theta. And then the angle of turn from the polar axis. So from that positive x-axis, which we now call our polar axis, that's going to be our theta. Okay, you could go counterclockwise or clockwise, and we'll have positive and negative angle measures. And I kind of just skipped ahead there. Sorry. So r is called our radial coordinate, right? That's our length, our distance from the pole, our origin. And then theta is called the angular coordinate. Now, theta can be positive, and that's when it's when it's counterclockwise, we're going up. And when it's negative, then it's going clockwise. It's starting by going down. Our radius can also be positive or negative as well. I'm sure you were just thinking, like, could r be positive or negative? Heck yeah, don't you worry. We'll get to that. All right, so let's jot some more things down. Unlike rectangular coordinates, x, y, polar coordinates are of the form r, comma, theta. All right, it's a terrible theta. So we want to plot 3, comma 60 by first drawing an angle of 60 degrees. Okay, so we have an angle of 60 degrees. That'll look something like that. I'll say that this guy is, 60 degrees. Cool. And then 3 for my radius, that'd be 3 units out. So let's just say that this is 1, 2, 3. So this would be 3, comma 60 degrees. And remember I said that it's out like it has concentric circles. You can kind of see down here already a preview. So that's what those arcs are for. It's like showing part of the circles that we're going to have here in just a sec. Okay? So, and I forgot to mention this, draw a ray. That's what we did. We drew a ray from the pole out at that 60-degree angle. Okay, now angles can be measured in either degrees or radians. We're going to deal mostly with radians here. We're starting out with degrees. I feel like it's a little more intuitive that way of like what the angles are, and then we'll slowly transition into pretty much just radians. All right. So the value of r, as I said, can be positive or negative. Okay. So when it says plot -3, comma 60, I'm still doing my angle measure of 60, right? So this is still 60 degrees, but my radius is now negative, which means that I'm actually going to, instead of going out, let me use a different color here. Instead of going 3 out like I did before, 1, 2, 3, and landing here, I'm actually going to be going 3 out this way, 1, 2, 3, and now that is my point, -3, comma 60 degrees. Okay, so I like reflect back. That's a good way of putting it. It's reflecting over the pole or over the origin there, back 3 for my radius. Okay, so that's my -3, comma 60, whereas this was my +3, comma 60 from the original problem. Okay, cool. Not a bad start here. We're gonna name some of these points in different ways here in this next example. And as you see, we have different restrictions for each part here. So we have point A right over here. In case you missed it, now it's circled in bright, wonderful pink here. We want to label that point with a positive radius, r being positive, and then our angle being between 0 and 2 pi. So we're in radians, okay? So what's my radius here? I've got 1, 2, 3, 4, 5 is my radius, okay? So 5 is my radius. That's a positive R value. And then my theta, well, between 0 and 2 pi, I've already got it 5 pi over 4. Awesome. Now the next one asks us to do negative radius, okay? And still between 0 and 2 pi. Well, a negative radius, remember, it would reflect back. So what if I were to think about like right along here? It's a little hard to see with the purple. Maybe I'll choose a different color, something a little brighter. How about orange? That's better. So I'm along there, right? And I know I was 5 out, so I'd be 5. Let's see here, 1, 2, 3, 4, 5. So I'd be sitting here at pi over 4, and then I'd reflect back to that point. So this would end up being negative 5, and then pi over 4. I'm in the restrictions. A radius that is less than 0, a negative radius, and then a theta that's between 0 and 2 pi. Love it. Fantastic. Wonderful. Okay. Next one, a positive radius, and then we want to be between negative 2 pi and 0. So I'm going to be a negative angle of rotation, but a positive radius. So that would mean I would do something like that, right, for my angle of rotation. So let's see here. If it's going to be a negative angle of rotation, that'd be negative 3 pi over 4 for my rotation there, but my radius would still be 5. So since it's a positive radius, I'd have positive 5 radius, but my angle of rotation was negative 3 pi over 4. A lot of you'll start thinking about like coterminal angles at times. So it will be with coterminal angles, but not always, obviously, because like this one up here, the orange one, it wasn't like a coterminal angle. It was reflected across that pole. All right. Next one, we have positive for my radius. So we know that's going to be 5, right? And maybe we're seeing that pattern now that, hey, like this is, let me fix that 5 there. That's a little better. Our radius is either going to be 5 or it's going to be negative 5, right? It's not like that number is going to change. It's our angle that's going to change possibly. So we want between 2 pi and 4 pi. So I am essentially doing a rotation here to 4 pi and then a coterminal angle, so I have to go around again. So I'm adding 2 pi to that 5 pi over 4. So I'm adding 8 pi to 5 pi because of the common denominator, and I'll get 13 pi over 4. All right. There we go. Made it through all 3 of those, or all 4 of those. I can count. All right. Number 9 here. Number 9. Let's go with a color we haven't seen yet. I'm going to go with red on this one since I haven't used red. I've used pink on this one, but not red. All right. Plot point B. So now we're going to have to plot it, not name it from, or not give the coordinates from the graph. So negative 3, comma 5 pi over 6. Now I really think about the angle of rotation first, and then I use my radius. So kind of at the same time. So I know I'm going to be at like 1, 2, 3. So 5 pi over 6 is right here at 3, but it's negative 3. So I really want to head back this way and reflect over that origin or over that pole to that spot right there. Boom. There is B. Cool, cool. So I went, again, I counted out 3. I went, wee, pew. There's my 5 pi over 6, but it was a negative radius, which means I had to reflect over that pole. All right. I like it. Good stuff. Fantastic. Now, it says, explain why every point in a polar coordinate system can be identified with an infinite number of coordinates. Woo! Infinite. I love infinity. To infinity and beyond, as one Buzz Lightyear might have said. So why can't it be? Well, case in point, I feel like this last one, or number 8 here, we could have done a coterminal, and that's only because I was restricted to that. I could coterminal all day, every day, so I could take my theta and I can add or subtract 2 pi over and over and over again, so it'll never run out, okay? Just like when we ask for what's a coterminal angle of this one, we always give you bounds because there's an infinite number of coterminal angles. So in that same regard here, there's an infinite number of ways we can name a point or give the coordinates of a point because of those coterminal angles. Awesome. Fantastic. All right, so now we're going to be doing some converting. So it can be helpful to be in one form versus another based on the type of graph that we're dealing with or the type of equation that we're dealing with. I really want to unplug that printer one of these days, but I won't do that. That would just be mean. Plus, I'd forget to plug it back in. All right, so we want to be able to convert from one to the other, vice versa, to be advantageous to us for particular types. There's problems way in the future that you're like, wow, that's so much better to be in polar, or that's way better to be in rectangular. We now have a little more tools in our mathematical tool chest. So let's see here. Use the rules for right triangles from previous coursework to evaluate sine of theta and cosine of theta. So what we're going to do is we're going to take what we do know and expand upon that. So sine of theta. Well, sine of theta, opposite over hypotenuse. That's what it's saying. Hey, use what you know. We know SOHCAHTOA, right? Opposite is going to be y in this case, right? And then my hypotenuse would be r. Cool. Well, hey, guess what? Didn't we have, let's see here, we want just y by itself and possibly just x by itself. So what if I were to multiply this by r? Now I have r sine theta equals y. I've got r and theta on the left side. I've got y on the right side. I've got polar action on the left side. I've got rectangular action on the right side. This seems like a solid conversion formula for me, right? I've got my polar stuff on the left. I've got my rectangular stuff on the right. That's all good, good. How about for cosine? Cosine of theta is equal to the adjacent over the hypotenuse. And by the same algebra, I would have r cosine of theta equals x. Again, I have my polar stuff on the left and I got my rectangular stuff on the right. These are two fantastic formulas, and we can go ahead and just jot them down formally here in this wonderful rectangular box here. Rectangular. All right, so I've got r cosine theta for x, and I've got r sine theta for y. Cool. I like it. And we're going to use this in our conversion process. There's ways to do it visually, graphically. We'll look at that, and we'll also connect that algebraically using these formulas on the next couple problems. So it says convert from polar coordinates to rectangular coordinates. So we're currently in polar, and if it doesn't have a little degree symbol, that means that it's radians, right? Pi over 4 is radians. Well, you know that. We look at like, oh yeah, okay, pi over 4, that makes us think radians, but does 5.5 make you think radians over here? Or excuse me, yeah, 5.5. You know, you don't really associate that, but there's no degree marking, so that's 5.5 radians. Let's hop to it. Okay, so we got a couple ways of going about this. I like to go visual, at least at first. So if I were to draw this one out, that was a terrible. I'll go here. There we go. That's good. All right. So pi over 4, that's a 45-degree angle, right? Pi over 4 be something like this. If we call that 10, well, it's a 45, 45, 90 triangle, so I would divide by root 2. Actually, we already dealt with that. We already dealt with 10. This becomes 5 root 2 and 5 root 2. So my rectangular coordinates are going to be 5 root 2, comma 5 root 2. How easy was that? Okay. Well, let's also look at it more formula-based for those of us that maybe like to set up formulas, right? X is equal to r, which is 10, cosine of pi over 4. Well, cosine of pi over 4 is root 2 over 2, isn't it? And then if we simplify that, 10 divided by 2 is 5 root 2. And the same would go with my y coordinate here for this one. Same exact algebra, and we get our 2. Okay? And there it is in case you wanted to see it. I figured save a little time in the video that way. All right. So we could go formula. We could draw a picture. It's really up to you. I'm a picture person, and I'm going to show you both. All right. So we get negative 4, comma 5 pi over 6. So 5 pi over 6, let's remember, is over here, right? But that's a negative 4, so really what's going to happen is it's going to come back this way for my triangle. And this is going to be a positive for radius then, if I'm thinking about this in my triangle here, and this is a pi over 6 reference, right? 30, 60, 90 triangle. So that would make this guy right here a -2, and this would be a positive 2 root 3. So as you can see, knowing your 30, 60, 90 triangle, your 45, 45, 90 triangle, that's super duper helpful here, knowing those sides. Otherwise, you got to do a little more tricky stuff and whatnot. So my rectangular coordinates are just 2 root 3, -2. Awesome. And if you want to go the more formula-based route, I would have x is equal to r -4 cosine of 5 pi over 6. All right. Now, cosine of 5 pi over 6, that would end up being, let's see, it'd be -√3 over 2. So I end up with, that's an awesome 3 there. I end up with positive 2 root 3 for my x, as we saw in our diagram, right? And again, the same thing, same process for y. And sometimes that actually helps to go with the formula route where you're like reflecting and things. Sometimes that can get a little bit confusing. And in case you wanted to see the y coordinate worked out, there we have it. Sine of 5 pi over 6 is positive 1/2 times -4 gives me the -2 that we got from our drawing. All right. Now this one, I'm going to draw it, but it's a little bit nasty here, you know, dealing with not so fun radians, right? Okay. So first off, I'm going to draw that a little bit better. There we go. 5.5. Where the heck is that? Well, how about this? Pi is 3.14. 2 pi is 6.28. It's going to end up being right all in here because 3 pi over 2 is like 4.7-ish. So it's right between there. So boom, awesome, fantastic. This is my radius, 16.2. My angle was the 5.5 radians. So now we got to figure out our missing side lengths if we want to draw this up. But they're not the nicest of, it's not like 30, 60, 90 or 45, 45, 90. Maybe I should just go straight formula based on this one. Let's do that. So how do I figure this out? Well, my x coordinate, if we remember, is my radius times the cosine of the angle. Okay. Now let me pull up my trusty calculator here. And let's remember something here. I got to be in, since I'm in radians, I got to make sure that I'm in radians. I am. Awesome. Always double check that before you wreck that. And so I can just type this straight up. 16.2 cosine of 5.5. Bada boom, bada bing. I've got 11.4804, so 11.480. And then my y coordinate, same idea, 16.2 sine of 5.5, which would end up getting me, I got it already worked out, negative 11.480. So my rectangular coordinates for this one would be 11.480, comma, negative 11.480. Awesome sauce. I like it. So that one was definitely more favorable to go the calculator route, the formula route, as it wasn't an easy triangle to draw. It was nice to have the position because you know what? It's also as good to double check. Like, do these coordinates make sense? A positive x value and a negative y, that does make sense. That does check out. So good stuff there, right? It's always good to double check those things that are easy to see. Okay? All right, convert from rectangular coordinates to polar coordinates. We want to plot the point -6, 0 on a rectangular coordinate system. So -6, 0 would be right there. Now it says superimpose the polar axis onto the system to determine the value of the angle and the number of units on the terminal side of this angle to get to the point. So in polar coordinates, what would this be? Well, my rotation would be That would be, it's a terrible arrow. Whoosh. That would be pi, right? That's a half a rotation. And my radius would be 6. So I would have 6 comma pi. You could also have, negative 6 comma 0. That would also work, right? I would be right here, and then I'd reflect that away. So either one of those would work. We'll go with that one for the main answer there, as we actually rotate the angle, and then we have ourselves a positive radius from that pull, from that origin pull when we're talking polar coordinates. Lovely, lovely. All righty, let's keep going. Convert from rectangular to polar. So we did polar to rectangular. We're in the rectangular to polar now. So the point 6, negative 6, and we've got ourselves a nice little graph here. So I'd be right down here, 6, negative 6. And the hint is to draw a triangle. I love me some triangles. So I've got negative 6 here. I've got 6 here. Ooh, that's a 45, 45, 90 triangle. 6 root 2. There's my R. Now, what is my angle? Oops, I don't want to have that closed off yet. What is my angle here? Well, my reference is 45, or pi over 4, but my angle of rotation would then be 7 pi over 4 to get all the way to that fourth quadrant, or 315. Or, I guess I could have even done this. Those would both be acceptable, right? Either one of those would work. Your call. It doesn't restrict theta to be between 0 and 2 pi, or negative 2 pi and 0. So really was dealer's choice on that one. When you're putting in answers into, say, like my math lab or on a test or whatever, we'll generally restrict the domain, restrict that theta value so that there's only one correct answer. Okay, next one. We got ourselves negative 3, 4. So negative 3 comma 4 would be somewhere right over here. If I draw my triangle, I've got negative 3, 4, right? Those are the coordinates, negative 3, comma 4 in rectangular. Oh, that's a 3, 4, 5 triangle. Look at that geometry for the win once again. 3, 4, 5 triangle. Okay, so I've got my radius of 5, but I need my angle. The angle that I want is this angle right there. That's what I want for theta. But a little bit of tricky trig can help me figure out this angle right here. How would I do that? Let's call that, I'll call that alpha for now. We'll call that alpha, okay? So if I want to find alpha as my angle, I would do, finding angles would be inverse trigonometry. I'll take the tangent inverse of opposite over adjacent, and that's going to be my alpha, which I'll use that to get my theta. Now, you might be saying, hey, Mr. Allen, why did you do positive 3? Now, you could do negative or positive 3. My reason for doing positive 3 is because I want to get my reference angle, okay? I want my reference angle. That's going to be easier for me to work with. So, if I do second tangent, 4 over 3, hit enter, I get 0.927 radians. What are my radians getting over to that positive x-axis there? Or sorry, the negative x-axis? That would be pi. So if I did pi, second pi, and I subtracted that 0.927, and I believe I could just go second ANS, I'd get 2.214 for my theta angle. So 2.214. Sorry for the change in color there, but I wanted to write it down before I forgot it. So again, we found our reference angle. We did pi minus that to get my angle of rotation, my theta, which is what I really wanted for this particular problem. But I used some inverse trig to do so. Inverse trig will help you solve for angles. I love it. Fantastic. Awesome. If you had rounded along the way, if you didn't go yo-ro, you may have gotten 0.213 instead of 214. So yo-ro, you only round once. All righty. Part C here. All right. So let's go ahead. We'll draw a picture again, right? This is the rectangular coordinate. It's negative, negative, which would mean it'd be somewhere around here, right? So negative 5.2 and negative 7.3. And I've got myself a right angle there. Perfect. And now what I want to do is I want to first figure out what's my r going to be? How am I going to figure that out? How about Pythagorean theorem? So I'd have 5.2 squared plus 7.3 squared is equal to r squared. And I'm not even worried about the negatives because I know that they're going to turn positive, right? I know they're going to turn positive. I've got this already worked out. It's 8.963. Okay, so there's my r. Now I need my theta. This is where the trig comes in, right? So I'm going to do tangent inverse. I want to get this angle first. So tangent inverse of 7.3 over 5.2. That'll give me my reference angle. And then in this case, since I'm moving past pi, I'll go pi plus that reference angle. And when we do that, we get, let's see here, we had 0.9518, so on and so forth. And if I add pi to that, I'm going to get theta is equal to 4.093-ish. So there's my angle, 4.093 for theta. Lovely, fantastic, wonderful. Woo! Love it. Fantastic. I keep saying that, but whatever. It is great. It's fantastic. All righty. I know we're getting a little lengthy with this video. Let's continue on. So this would just be our general summary here. A nice, beautiful thing to screenshot, save in your, pop it in your Snapchat story, whatever you might want to do there. So very helpful things. Look, we even got our find your theta, right? Tangent inverse action, our different formulas solved. Feel free to pause it, jot all this down if you want in one snapshot. Otherwise, I'm going to keep on moving and grooving. I know this is a long one. I apologize, but thank you guys for sticking around here. Thank you for sticking around. I mean, you are forced to, but whatever. All right. So now converting rectangular and polar equations, not just coordinates. So transform the equations from rectangular to polar form. All right. So these are rectangular forms for their first examples. Polar equations, remember, those have r and theta, right? And they can be derived from our rectangular equations by two different techniques, generally. Replace the x with r cosine theta and y with r sine theta. And also replace x squared plus y squared with, it should say r squared right there. So r squared. So let's go ahead and do that. Shall we? I think we shall. So let's see here. We've got x squared plus y squared in this one. So that would be r squared equals 25. And we're going to square root both sides. So we should usually have like r equals or something like that. I'll get r equals plus or minus 5. Beautiful. Fantastic. All right. That's just a circle centered at the origin with a radius of 5. And in our polar coordinates, same deal here. Okay. It's a circle with a radius of 5. That's literally what it is. All right. Part 2 here. This one's a little bit messier. So first things first here. I'm actually going to FOIL out the x minus 2 squared. Remember, that's not x squared plus 4. We got to FOIL it. All right, so with this next thing, we're going to go x minus 2 times x minus 2. Don't worry, I had to strap up, common space. Sometimes people don't need to use this space. So we get x squared minus 4x plus 4 plus y squared equals 4. Woo! I love it. Notice my x squared and my y squared. Guess what x squared plus y squared is? That is r squared. I'm already replacing. What do we know about x? X is equal to r cosine theta. So I can replace that x with r cosine theta. Then we have plus 4 equals 4. Lovely, lovely. And now I have r squared. Ooh, these 4's cancel. Nice, nice. Minus 4r cosine theta equals 0. All right, and now at this point here, we see that we have an r in common. So we have r times r minus 4 cosine theta equals 0. Well, r equaling 0, that would be a circle with a radius of 0, which isn't a thing, right? So what we are left with is r minus 4 cosine theta equals 0, so we'll have r equals 4 cosine theta. That will be our final wonderful, beautiful equation on a graph that would actually look like a circle centered at like 2 right there with a radius, or excuse me, a diameter of 4, a radius of 2. All right? So we'll get into graphing a little bit more later, but that is what it would look like scooched over. And actually that does play off of our original rectangular form as well. All right, if you remember how to graph circles in rectangular form. All right, so now going back the other way, transform the equation from polar form to rectangular form. Rectangular equations are those with the x and the y, right? So we want to get x and y into these. All right, we're going to get rid of the r's and the thetas. There we go. All right, so method 1, square both sides. If I were to square both sides here, I'd have r squared equals 25. And what do we know about r squared? That's equal to x squared plus y squared. And bada boom, bada bing, I am in rectangular form. Beautiful stuff. I have to applaud Miss Fuhrer in here right now. She is being she's trying so hard to be quiet. And I do appreciate it. I do appreciate it. We're just going to keep mathing though. Don't you worry. People are so courteous around here. So, because I'm in a common space, you know, it is what it is. All right, multiply both sides by r is our other option, which on the left-hand side will result in the same thing as squaring both sides, but not on the right. So if I multiply by r on both sides, r and r, I've got r squared is equal to 4r sine theta, and I put the r in that position for a reason. If you remember, r sine theta, that's equal to y, so I get 4y, and I know r squared is x squared plus y squared. Look at that. That's beautiful. I'm going to set it all, I'm going to get that equal to 0. I'm going to bring everything over, and that will be my final answer. And we get this wonderfulness. X squared plus y squared minus 4y equals 0. That is acceptable. You could go through and complete the square, which, you know, to each his own. But I will pop that work up there in case you want to see how you would complete the square. But this will be just fine for entering into my math lab. Actually, I'm not even going to put that in there. This video is already long enough. Thank you guys so much for hanging out. You know, remember, yo-ro, especially when calculating those angles, right? We're going to get into some graphing here soon. It'll be awesome. American Freedom, Rock and Roll Costco, and, of course, Riverdog Jenny on the gram. See ya.